We finished up our last lecture starting our conversation about our senses. Um, that's where we'll pick up today. Keep in mind that you're going to need those documents that I spoke of in the last lecture. If you go to your exam 3 folder, there is a Word document that's entitled Special Senses. You'll want that. Definitely want that. And you may well want the Special Senses PowerPoint slides. Those are the diagrams that I'm going to use to overlay those two documents together. Right now, when we talk about our senses, you'll notice that we're not being specific to vision, hearing, taste, those things. Okay, we're being relatively vague here because we have to remember when we talk about our sensation, we're talking about external conditions, but we're also talking about those internal conditions that I've been trying to stress to you. Stretch receptors that are called baroreceptors, proprioceptors, which give your body an idea of where it is in space and time. Chemoreceptors that monitor carbon dioxide level, glucose level, those sorts of things. Right? So we have to keep in mind that we're kind of broad here when we're talking about our senses. We'll narrow it down a little bit in a bit, but right now we're kind of broad. Now, these sensations have characteristics. The first is projection. Projection means that it's the process by which the brain refers sensations to their point of stimulation. This is kind of messed up, folks. Students often get kind of freaked out by this. If you stub your toe hurts, or you know that your toe hurts because of this projection. Because there's information being sent from your toe to your brain saying, ow, that you just whacked the heck out of that. That hurts, and your brain sending a signal to your toe telling you that that is in fact where the pain is coming from. So that's what we mean by projection. We're sending that sensation to the point of stimulation. That's why you know when somebody's touching you, even if you can't see where they're touching you, right? Because of this concept of projection. Adaptation is a decrease in sensitivity to continued stimuli. Febreze has used this concept for a fairly successful ad campaign. And I know most of you don't watch commercials, but you might have caught this one. It talks about being nose blind, where you walk into somebody's house or you walk into your own home and you don't smell the cat litter. You don't smell the wet, dirty dog because you just don't smell it anymore. Well, that's this concept of adaptation. I have lots and lots of examples. That's a really good example that we've used successfully in an ad campaign. Another one would be if you go to somebody's house and sleep over and they have a drippy faucet. That first night, it's like they're banging on your forehead. That's all you can hear, and it kind of disrupts your sleep. After a while, you don't even quote unquote hear it. Oh, is it still dripping? Well, yeah, it is, but your body, evolutionarily, your body tunes out stimuli, sensations that are not of relevance. So if you're not going to do anything about that dripping faucet, your body's like, okay, it must not be anything to worry about. We're just going to ignore it. Right? So that's what we mean by adaptation. Another good example is if you come home and you can smell gas in your house and you kind of walk around and you're like, okay, the stove isn't on, the furnace isn't doing anything weird. And after a little bit, you're like, oh, I guess maybe I don't smell it anymore. That's how people die of gas poisoning, because of adaptation. Your body gets accustomed to it and no longer sends an alarm. So it's still there, you just can't smell it. But if you were to go outside and come back in again, you would smell it. Another sensation is after images. These are where the sensation persists after the stimuli has been removed. Again, I've got a couple good examples for you. You might not know this. I just love the beach. Anytime I can get to the beach, that's where I want to be. And one of the things I love to do is stand in the break line where the waves are breaking. And I'll stand there so long that After I'm out of the ocean, oftentimes when I'm kind of trying to fall asleep, I can still, quote unquote, feel the waves coming in and out against my legs. Well, I'm miles away from the ocean. There's no water in my bed. However, I can still feel, quote unquote, feel that sensation. Another example is if you've been to a concert, right? You've heard live music, and it's very, very loud. And even after the band has stopped playing, you can still kind of hear that sound. That's an after image, right? So the sensation persists after the stimulus has been removed, after the stimulus has stopped. The last is modality. This is the specific characteristic which allows each sensation to be distinguished from one another. How is that sensation processed? There's a different set of quote unquote wiring, a different set of neurons that are going to carry visual stimuli, chemical stimuli, pain stimuli. And that's going to direct it to the specific part of the brain to process that information to give us the correct information, right? That's why sometimes people will say, if they did LSD, that they can taste colors, okay? They can smell colors. Because of the effects of the drug, it's altering this modality, right? But in fact, it's false, but it's changing your perception of this, of how the wiring is happening in your body. Here's where you're going to be a lot more comfortable, and that is with the special senses. The special senses are typically, as humans, what we think of when we talk about senses: vision, hearing, taste, and smell. Now keep in mind, everything we've talked about previous to this slide applies to our special senses, right? We're just pulling these out to talk about them because these are a lot of these organs we're going to talk about in lab, and these are the senses that we're pretty much most familiar with. The two that we're going to focus on are vision and hearing. We'll start with vision. We need an eye in order for vision to happen, but it's not just an eye. We need an eyeball that's going to measure about 2.5 centimeters. That's a little bit over an inch in diameter. And that eyeball is made up of 3 layers or tunics, which we'll talk about in subsequent slides. However, in order for vision to happen, we also need the optic nerve, this second pair of cranial nerves, and the occipital lobes of the cerebrum. If you remember when we talked about the function of our different lobes of the cerebrum, when we talked about the occipital lobes, it was visual interpretation, determining what that information was that the eye is bringing to that lobe of the brain. Now, the layers of the eye, this is going to be helpful to you for lab content. As we say, the eye is made up of 3 layers. We're going to start with this most superficial or the outermost layer, and that's called the fibrous tunic. Now, a tunic is just a fancy word for a layer. And in 132, we talk about the layers of the blood vessels, and we talk about them being tunics, all right? And it simply is a fancy word for layer. So the fibrous tunic is going to be the outermost layer of the eyeball. And it shouldn't come as a big shock to you that it's going to be made up of fibrous connective tissue. We could have guessed that by looking at the name. The fibrous tunic is broken up into different parts. The first we're going to talk about is the sclera. This is the posterior most portion. This is the white of your eye. It is a white coat, a white layer of dense connective tissue, and it gives shape to the eye. If you use contact lenses, you know that your eyeball is kind of pliable. It's kind of squishy, if you will. The sclera helps to keep the eyeball's shape and to give it a little bit of toughness so that it's not kind of oozing out. Also part of the fibrous tunic is the cornea. The cornea is non-vascular. There are no blood vessels. It is transparent, and again, it is also made up of fibrous connective tissue. It covers the iris of the eye, so the cornea is going to be the anterior portion of the fibrous tunic. Again, if you wear contact lenses, you're taking your contact lens and placing it on the cornea of your eye. So that's where that's going to be. Now, the conjunctiva is an epithelial layer, a wrapper, a membrane, if you will, that covers the sclera, not the cornea. Now, let's talk about the cornea for a second. Why wouldn't I want my cornea to be vascularized? Everything else we're very interested in. We want there to be blood vessels, and that's going to help with healing, and that brings nutrients and gets rid of waste. Why don't we want the cornea to be vascular? Well, if we think of where it's positioned in the eye, that's what you're looking out of. That's where the light and information is coming into the eyeball through. So if there were vessels, it would be like looking through a massive spaghetti. There would be all kinds of lines in front of your field of view, and that would be problematic. That's why we know the conjunctiva only covers the sclera. If you have an inflammation or infection of the conjunctiva, you have conjunctivitis or pink eye. Think about where your eye becomes pink. Just on the white section, not the cornea. Right? So that's how we know where the conjunctiva is going to be located. Now, when we look at this diagram, the white outer edge is the sclera. Toward the front of the eye, it's kind of a pale greenish. That's going to be our cornea. Those two layers make up our fibrous tunic. Next, we're going to talk about our vascular tunic, and that's that red section. This diagram sometimes gives students fits. You have to realize that we've peeled down the yellow layer. That's the innermost layer. We've peeled it away, and we've peeled away the red layer. So what we're seeing is the innermost layer is the yellow, the middle is the red, and the outer is the white. So the fibrous tunic is the white layer. Our next layer is the red. That's going to be our vascular tunic. As we said, this is the middle layer of our three tunics that are going to make up our eye. The vascular tunic is made up of three parts. First, we have the choroid. It is a thin, dark brown membrane. This color prevents the eye from kind of ricocheting around your eyeball. If you've ever worn a dark brown shirt or a black shirt out on a very, very sunny, warm day, you know that dark colors absorb light. And that's what we want here. We want this dark brown membrane to absorb the light so it's not causing havoc. It's not giving you little flashy things in your eyeball to get in the way of what you're really seeing. It lines most of the internal sclera. It is highly vascularized to nourish the retina. The retina is the innermost layer. The retina is made up primarily, almost exclusively, of neurons. So again, we have to have a way to get nourishment to our neurons, and that's where our choroid comes into play. The ciliary body is also part of the vascular tunic. Its job is to hold the lens in place. From our ciliary body, you're going to see suspensory ligaments. In most diagrams, they look like little threads that attach directly to the lens. Those suspensory ligaments are then held in place by the ciliary body, and that's why we say that it holds the lens in place. Next, we have the iris. The iris is made up of muscle fibers. This is what gives your eye color. For me, my iris is a blue, so we say that I have blue eyes, all right? The iris controls the size of the pupil. Because it's muscular, it can contract or relax, changing the diameter of that hole of the pupil. It's going to determine how much light enters the eye.